Okay, in this video, we're going to talk a little about the basic comparison test and the limit comparison test. So these are tests that allow us to determine series convergence or divergence if we know a kind of another series that is a little bit more well behaved that we can compare it to. So we consider a sum of a sub n that we wish to determine the behavior of, and we in particular take an to be greater than or equal to 0. So take an to be positive for all n. We can compare this sequence with a similar sum. So we can take the sequence an and compare it to another sequence bn that is either where the sum of bn is easier to determine the behavior of. And so our idea is if an is less than or equal to bn eventually, and bn converges, then an has to also converge. So I drew this picture here, I made this picture here where we have, these are the terms, these black dots are the terms of bn, and we know that an has to be less than or equal to them, right? But still greater than 0. So an has to be somewhere in here. So in a sense, the sum of an is bounded by the sum of bn, and the sum of an has to converge with max value the sum of bn. Similarly, if an is greater than bn and bn diverges, then an must diverge. So if these black dots are the terms of bn, and we know that an is larger than bn, it's somewhere over here, and bn just goes off to infinity, then we know that an is forced to go off to infinity with it, okay? All right, so let's look at some examples. So I have 1 over k to the fourth plus 3. So I don't like this sum, right? Because I don't know exactly how to determine convergence of it, but I noticed that it kind of looks like the sum from k equals 1 to infinity of 1 over k to the fourth, right? Very similar. And I know that how to determine the convergence of 1 over k to the fourth, right? Because it's a p-series. So this converges by p-series. By p-series. Right? P is equal to 4, strictly greater than 1. But I don't know the convergence of 1 over k to the fourth plus 3. So I can compare them. And so all I need to figure out is if an, which is equal to 1 over k to the fourth plus 3, and bn, or 1 over k to the 4, are related in the way that I want them to be. So by my basic divergence test, I want bn to be larger than an, because it converges. I need it to bound it above. And it is the case that bn is, or in this case bk, right? I say n, but we want bk, because we're indexing with k. It is the case that this ak is smaller than bk, right? Because 1 over something larger is smaller. So I do have that this basic divergence, or basic comparison test, Lord, will work. So because this converges by p-series, I know that the sum from k equals 1 to infinity of 1 over k to the fourth plus 3 converges by basic comparison test. Okay, so it's just a little exercise in logic there. Another example, ln of n over n cubed. So let's let an equal ln of n over n cubed. And this kind of looks like the sum from n equals 1 to infinity of 1 over n cubed, right? Or maybe we look at n over n cubed, because this is just 1 over n squared. So let's let bn, I know that ln n is less than n, right? So if I think about the graphs here, this is n, this is ln n. Ln n is always smaller than ln n is always smaller than n. So I can write bn equal n over n cubed. Then this is 1 over n squared. And I know that because ln n is smaller than n always, I have that this is going to be strictly less than. And I know that this will converge by p-series. So the sum of 1 over n squared converges by p-series. So p equals 2 greater than 1. And because of that, I know that bn is larger than an. We get that the sum of ln of n over n cubed converges by basic comparison test. Great. Okay, so we can always compare ln to n. We can always compare ln x to x. We can always compare ln n to n, right? So it's a fair comparison because we always know that ln n is smaller than n. Okay. Next thing we want to look at is limit comparison test. So limit comparison test works a little bit better in my opinion. For certain situations, it might be a little bit overkill for others. But our idea is we don't need to know if an is larger or bn is larger. We only need to know about the limit of their ratio in order to determine how they will behave. So if we have a sum an and we have another sum bn, and we know that bn has this behavior, maybe it converges, maybe it diverges, but we know what it does. All we have to do is look at the limit as n goes to infinity of an over bn, and that'll help us determine what the behavior of an must have been. So if their limit is non-zero and finite, then they both converge or diverge. If the limit is 0 and b converges, then a converges. If L goes to infinity and bn diverges, then a diverges. Okay? So those are our three conditions. Get familiar with those, but let's apply them here. So n over n squared plus 1. So an, we're looking at n over n squared plus 1. I feel like a fair comparison would be bn equals n over n squared, just n over n squared, right? Right, so pretty close. So let's do our simplification here and write this as 1 over n. Okay. So yeah, let's do this comparison. And for the limit comparison, what we care about is the limit of the ratio of an over bn. So let's take a look at that. The limit as n goes to infinity of an over bn is equal to limit n goes to infinity n over n squared plus 1 times, I'm going to go ahead and just do the keep change flip, so n over 1, right? Because if I have a over b over c over d, that's the same as a over b times d over c. So I just went ahead and flipped it already. This is the limit as n goes to infinity of n squared over n plus 1. Sorry, n squared plus 1. N squared over n squared plus 1. And you should know that that limit is just 1. So it's non-zero and finite, so they have the same behavior. We know that the sum of 1 over n diverges because it's the harmonic series. Therefore, the sum of n over n squared plus 1 diverges. We just showed by the limit comparison test. Okay, good. So moving on, let's look at the sum from n equals 1 to infinity of 3n plus 1 over 2n minus 1 to the 4th. Okay, so my an is going to be 3n plus 1 over 2n minus 1 to the 4th. How about we pick bn to be 1 over n cubed? If I pick bn to be 1 over n cubed, I know the convergence of this. This is going to converge by p-series. Then the limit as n goes to infinity of an, which is 3n plus 1 over 2n minus 1 to the 4th, times n cubed over 1, so that's an over bn, is going to be 3n to the 4th plus n cubed over 2n minus 1 to the 4th. The limit of that. Okay, well, when my powers are the same, and they are, so the degree of the denominator is the same as the degree of the numerator, I just look at the leading coefficients. So this is going to be the same as the limit as n goes to infinity of 3n to the 4th plus whatever, doesn't matter, I'm only looking at lead coefficients. And then this is going to be 2 to the 4th is 16, n to the 4th plus whatever, doesn't matter. So this limit is going to be 3 over 16. So it's non-zero and finite. So that tells us that an and bn have the same behavior. So because the sum of 1 over n cubed converges, by p series, the sum of 3n plus 1 over 2n minus 1 to the fourth converges by limit comparison. Okay, and that wraps up what I want to say about limit comparison and basic comparison. And if you found this video helpful, please consider liking and subscribing. Thanks.